Hi, everyone. My name is Paritosh Mukhasi. I'm a kernel developer at the Algorithms R&D division. I hope you guys got a chance to listen to Nina's talk, which was just before mine, wherein she went over some of the details of the new capabilities that we have for solving certain kind of optimization problems. So today I'm going to be focusing on what kind of problems we can solve that go beyond convex optimization. So just to give you guys a quick recap, convex optimization, when we talk about convex optimization problems, we're talking about solving a problem of the kind you have a function which you would like to minimize, and you have a set of constraints. And the special thing about this optimization problem is that all the functions are convex in nature. And by that, what I mean is that it satisfies this inequality over here. And this is a very powerful inequality that assures us that when a convex optimization problem is solved and you reach a minimum, you're assured that for that specific convex problem, you're going to get a global minimum, and that is extremely helpful. And we have had convex optimization features since version 12, and so you can specify your constraints in a variety of ways, and I've listed these over here. Nina also listed them in her presentation. But this kappa over here is called a convex cone, and this could take the form of a non-negative cone, norm cone, semi-definite cone. And so you have a whole list of convex cones that our optimization method framework supports. But what I would like to talk about is going beyond convex optimization. So there will be two things that I'll be covering in quite a bit of detail. One is quasi-convex optimization problems, and difference of convex optimization problems. So let's start off with quasi-convex optimization problem. So it's quite similar to the convex problem with one slight difference, which is that your objective has a form that is quasi-convex, and what I mean by that is that objective function satisfies this Jensen's inequality. It's this property. So instead of that alpha plus beta that you saw in the previous couple of slides, which is this, you now have that max term over here. Here's a sort of like a graphical representation of what I mean by that inequality, which is that you'll notice that in this caricature of a function, the function will sometimes it'll have a slump, and then it'll go back up. So this is not a typical characteristic you would assign to a convex function. Nonetheless, these would be classified as quasi-convex problems. And as long as, so there are certain properties that quasi-convex functions have, and I'd like to quickly go over them because we are going to use, or rather exploit, the properties of these quasi-convex functions in order to solve quasi-convex problems. So what are the quasi-convex function properties? The first one, the most important one, is a function is called quasi-convex if all the sublevel sets for a specific value of alpha are convex. And it's got this definition associated with it. And if you're not familiar with how to interpret this, I'll be going over. We'll be using this exact this property in order to actually solve the problem. And so you will see this in a programmatic fashion in the next couple of slides. The other couple of properties is that the function is either non-decreasing or it's non-increasing, and it'll always have a point C such that if it's on the left, it will be non-increasing. If it's on the if it's greater than C, then it will be non-decreasing. So these are some of the properties that are associated with quasi-convex functions. Okay, so in a theory, let's see how is it that we actually solve quasi-convex problems. Okay, so the so you could solve this using our n-minimize function or even convex optimization function. In this presentation, I'm going to very heavily use n-minimize function. So just to give you an idea, n-minimize actually hooks up to the convex, the optimization method framework in order to analyze if the problem is quasi-convex, convex, etc. And if it classifies a certain problem as quasi-convex and no method is given, as a method is automatic, then it moves it over to specialized quasi-convex solvers to solve the problem. So now internally we have two functions called quasi-convex bisection and quasi-convex subgradient, and I'll talk about the algorithms associated with both of them. So for the excuse me, for the toy example that I wanted to use to illustrate these two solvers, we're going to take this this x times y objective. This x times y is a concave function, but negating that makes it a quasi-convex. And we give it certain constraints, non-negativity constraint and a norm code constraint. Okay, and this when you run it, it n-minimize solves this. Internally, if you were to specifically give quasi-convex bisection or quasi-convex subgradient method, you get similar results. But you'll see slight differences in them, and those are to be expected. But we'll delve into the nuances in a bit. So just to give you a visual idea of what is the objective, what does the objective look like in this convex set? This is your negative x times y, and what you have are these contours, and these contours can be thought of as level sets. And so you remember when we talked about those sub-level sets? Well, they are technically when it comes down to the programmatic part of it, it's just basically these level sets, these numbers here. Negative 1.1 would be a specific value of that alpha, negative 2.2, so on and so forth. So the objective of, so the way quasi-convex bisection method works, and we'll get into that right now, is that we are going to find a specific alpha for which the problem, when you give that specific value, the sub-level set value will produce a feasible solution. And if you give another value, it will give an infeasible solution. And once you have established those bracket of feasible and infeasible solution, then you can just start refining that bracket using the bisection method, and you'll be able to get to the solution. So that's the basic premise of that. And so I have put together a very simplified code. Obviously, internally, we're doing a lot more, but this should help demonstrate the point. So what we do is we generate a parametric function, and that parameter is your sublevel set alpha. Okay, so we generate that, and now for this particular problem, I've taken if you go back to the graph, you'll see that -2, it's definitely within the convex set. But if you move back, you'll see that -4.4, you're reaching the edges. So that's why I chose -5 over here. Okay, and when you solve this, the convex optimization basically says, okay, for -2, yeah, you do get a feasible solution. Now, remember, we are not interested in finding a minimum point. We want just a feasible point. So you see the objective here that I've given for parametric convex optimization is 0. Okay, so it can choose any point on that level set. And the idea is that as you keep on doing this bisection, the closer and closer you get to the optimal solution, your feasible region becomes like a feasible point, essentially. Okay, so now you take your lower bound and your upper bound, and we'll just apply the bisection method like for 10 iterations. And in doing so, you see that -3 so you initially it bisects that, and then it refines while maintaining the feasible, infeasible bracket, and eventually converges to a solution. Of course, if you iterate even more, you'll get closer and closer to the optimal level set. And once you get to that optimal level set, then you can get the primal minimizer vector, which becomes your solution. So that's basically it. Underlying, it's a very, very simple algorithm. You can look at some of the papers published by Boyd that talk about this. It's literally 5 or 6 lines of basic code to get this working. Okay, the second method is subgradient method, which is in some sense even more simpler. The idea is basically you start with an initial starting point, and then you basically go down the gradient, go down in the gradient direction. And so it's called subgradient method because sometimes the function may not be differentiable, in which case you have to take sample points and get an approximation of the gradient, which is what is called a subgradient method. In our case, they're all continuous functions, and the gradients are available. So this subgradient is actually a gradient method. So G becomes your gradient, and you'll notice this thing over here, this projection operator. And the reason you want to do this in this update in this fashion is because once you take a step in the descent direction, there's a very good chance that it might go out of the convex set. So you want to pull that back into the convex set vicinity. And so that's why, so technically the correct name for this approach is the projected subgradient method, because at every iteration you're providing a projection step as well as a descent step. Okay, so just to remind you, this is the n-minimized problem we're trying to solve. We are going to set up a parametric convex optimization function which does the projection. So if you have P, so given a P, given a Q, you want to find a P that lies inside the convex set, or at least on the boundary. Okay, so let's give the reference solution. That's a parametric function. And so now we have our function, which is negative x times y. And then we have, I've manually entered what the derivative is going to be. Okay, and then you basically just run it through that. So at the very first step, we'll project it. Then we take a step, and this is the step length, this part, and that's your gradient. And then you just iterate it. So I've performed the iteration 30 times. And the best way to visualize this is using the contour plot and just seeing the path that it took. So notice that I started with 1, 1.1, which is around here. So, and then it takes around the 30 steps, it hits the boundary of the convex set, and then it travels along the convex set boundary till it reaches the optimal solution. So nothing complicated. These are very straightforward, but quite robust algorithms when it comes to solving quasi-convex problems. Okay, moving on to difference of convex. Now, difference of convex is a special kind of beast in that you end up with functions that are not necessarily convex, but if you were to analyze them, separate them out, then you could write them as the difference of two convex functions. So the problem that we intend to solve would be you want to minimize f and minimize this function, which is written as a difference of convex. So f and g are convex functions, and the constraints themselves could be difference of convex. So f and g, fi and gi being convex, right? So, well, the difference of convex can end up giving you really funky domains. Like, for example, here's a domain. This is definitely not convex. It's got a hole in it. There's stuff going on. So like, for example, this norm, or let's look at this one. Norm of xy less than or equal to 3 is convex, but norm of xy greater than or equal to 1 is concave. So in order to represent this as a convex problem, you negate it, and so you end up with negative norm xy less than or equal to -1, and that's how you would get the difference of convex. Okay, so what are some what do simple examples look like? So here's an example wherein you have a convex set, but your objective is our difference of two convex functions. So this would get classified as a difference of convex problem, and it goes off and solves it using the specialized solver. So in this case, that's your that's your minimizing point right there, -4. Okay. Here's an example wherein your objective is convex, but you have a convex constraint and a concave constraint, so this gets transformed into a different. So this constraint gets transformed into a difference of convex problem. So when we solve this, we get a result, and over here is the minimizing problem. Okay, so what are we doing behind the scenes? I guess that's it. All boils down to what are we doing behind the scenes that allows us to solve these kind of problems. So let's go back to this second problem, and I will try to walk you through the steps of what's going on behind the scenes in order to solve problems like these. Okay. So the strategy is pretty straightforward. You take your difference of convex function and you approximate it by linearizing the second term. So if your difference of convex function can be written as f of x minus g of x, you take the g of x and you linearize that. So you take the gradient so you start with the starting point, take the gradient of that, and replace your original function with this function. Right? And this function is going to be a convex function. And once you have converted all of your difference of convex functions into convex functions, then you have at your availability powerful convex optimization solvers that solve that give you a result very, very quickly, and that allows the iteration strategy to proceed. Okay, so once again, to remind you, this is the problem we're solving. Okay. Here's the counterplot associated with it. So obviously we are going, we want to get to 0, -2 over here. So let's see how that happens. So the first thing we do is we generate a parametric convex optimization with some minor differences. The first thing is you'll notice that the objective now has this term here. It's W times alpha over here. So what are these two terms? I'll explain that in a bit. So the first convex constraint is left as it is. The concave constraint, which is norm of x, negative norm of xy less than or equal to -1, gets transformed into this linear inequality constraint. And then you have this alpha, and alpha is greater than 0. So this alpha gets tacked onto the linearized constraint. And the reason for that is because if you don't add this this quote unquote slack in the original problem, then there's a very good chance that your function, that your convex solver might not be able to get a feasible solution. So what we do is we start off with an alpha. We let alpha take some arbitrary value, and then what we do is we slowly ramp up this W value. So W is user defined, and we slowly ramp that up. And because alpha is greater than or equal to 0, alpha has no choice but to go as small as possible. And when alpha is equal to 0, we know that everything is tightly within tight bounds. So that's the basic strategy. So the parameter, so this is the parametric function, and so it takes the initial starting value for x and y, and it takes an initial value for w. So in this case, I've decided to give it 0.5, 1.1, and a weight of 1. Okay, so 0.5 is around here, 1.1 here. So the starting point is over here. So let's see what happens when we run this. We get a value of 0.2, -1.8. So it's already coming pretty close to it, but alpha now takes a value of 2.7. So if I were to now do pfun 0.2, -1.99, and alpha, let me just keep it at 1. What I do is 0, -2, right? Now I can already alpha is a pretty small value, but I could just as well ramp this up to 100, and it'll bring the solution closer and closer to it. These difference of convex problems, because of this strategy, allows the pretty rapid convergence. So typical problems within 4 or 5 iterations, you end up getting very close to the optimal solution. So let's jump into some application examples. So the first one, which is kind of cool, is we have a path planning problem. So you have a start point and an end point, which is, and you have all these obstacles. And so the objective is for you to go from point A to point B while avoiding all the obstacles. You can't go through them, right? So how is this modeled so that you can solve it using difference of convex problem? Okay, so what we do is we are going to, our continuous path, we are going to discretize it into 30 separate instances. And each one of those points will obviously have a certain constraint associated with it. The first one is going to be that no 2 points should be too close to each other. So we'll call that a distance constraint. No point that we have discretized point should lie inside those specified objects. So we'll call those object constraints. We have to specify the starting and the end point, which is x of 0 and x of n. And after that, all we do is we need to collect the variables. Okay, so that's where we are collecting the variables. Now, I would like to point out that the difference of convex constraints come through these object constraints, because we want it to be outside of the circles, making it a difference of convex problem. And here's the solution. I'm going to run this. It will take a couple of seconds, but you eventually get a result. Yeah, I'm pretty sure we got the result. And then when you plot the result, you see that it swerves around the obstacles and goes from the start to the end. So this obviously has got great applications. You could represent arbitrary objects as you could provide bounding boxes in terms of a bounding ball for arbitrary objects and use this for path planning while avoiding obstacles, for example. Okay, let's go for a second example. This is a geometry-based example wherein the known is that we have a bunch of circles and we know the radius of these circles, and we would like to fit them in the smallest box possible. Okay, so in this particular example, we have n equals to 20. We have 20 circles. These circles have random radiuses, and the objective is to pack them together so that there is no overlap. There's no overlap between any 2 circles. The circles will just touch each other, and we want to find the smallest bounding box associated with it, right? So I won't go through the technical math behind it, but suffice to say that it's basically we are minimizing the maximum value associated with all the centers and the radius. So the objective is transformed into constraints. We add the difference of convex constraint, which says that the circles must not overlap, which is what you see here with the greater than or equal to, with the norm on the left-hand side. And you basically then go ahead and collect all the variables and then go ahead and solve the problem. This takes a few seconds, but we eventually get a result. And what you see, what the objective is giving you is telling you that those are the coordinate bounds associated with the square that encloses all these non-overlapping circles. So that's S is actually, these are the coordinate bounds associated with it. So when you plot it, this is what it looks like. Now I hope that this is obvious that this is not a unique configuration. This is a configuration. If I had used different starting point or maybe changed the parameter or some weight, then I would get a different configuration, though the bounding box would still remain the same, or it might be even smaller. So, these are certain examples of what you can do with difference of convex. I'll give you one more example. This is a pretty simple one wherein you'd like to do data fitting. You have a matrix A, vector B, and X can only take a value of -1 or 1. Okay, so this is so we'll just make up some random matrix and vector, and we have a reference solution, which the vector B is a dot xref plus some kind of noise. So we are doing some kind of data fitting. But the important thing is that this constraint -1 and 1, it can get modeled as x squared equal to 1. Now, x squared equal to 1 is not convex, but if you write it in this form, then it can be separated into a convex part and a non-convex part, and the non-convex part is the one that gets modeled / transformed into a difference of convex problem. And so here's the result. And if you compare that with the xref minus as 2, it's all zeros. I mean, I could just round this up and it'll say, oops. It's all zeros. So these are just a sample of the problems that can be used to solve these kind of to solve a much wider array of optimization problems. So so this basically concludes my talk. I do want to point out that there is still a lot of new functionality that we are working on that will come in. There's stochastic, global, all these various kind of optimizations are going to be made available in future versions. So I would highly recommend that you go start playing around with it, and we absolutely would love to hear from you to see what kind of problems that you're trying out, and if you're running into issues, we would definitely like to know those things. We do have office hours tomorrow morning. So if I can't answer your questions right now, we can probably pick it up during the office hours tomorrow. So with that, thank you for your attention. I hope you found this interesting, and I'll try and answer some questions from you guys. Okay, so the Mathematica notebook has been uploaded, so you should be able to see that under files, Yuzo. Robert. Yeah, I know. I just like to make the life difficult. But you're right. CHOP would have been the right thing to do. Duly noted. Thank you. Yes, Nick. That's a very good point. I think there are even some specialized softwares for doing that, because if you can get the circle packing problem addressed, that is a great gateway into doing quality meshing. So you're absolutely right. It's a very active area of research, and it's closely related to Delaunay triangulation, Voronoi meshes, etc. So yeah. Thanks, Oliver. I hope that this was informational. Thanks for it. Well, I think we're almost out of time here. Once again, like I said, we have office hours tomorrow. Oliver, Nina, and I will be there. I think it's at 10 o'clock. But please do double check. And yeah, if you have some specific questions, we'd be happy to have a conversation tomorrow. But if not, if there's no other talks or any other questions, then I wish you all a very good evening, good morning, wherever you guys are. And I'll see you guys tomorrow. Have a good one. Bye.